Close your eyes, take a slow breath. The oxygen entering your lungs right now was created billions of years ago inside a star that no longer exists. That star lived for millions of years, burning hydrogen into helium, fusing atoms in its core under pressures and temperatures we can barely imagine. And then it died. It exploded in a supernova, scattering its contents across space. Carbon, oxygen, nitrogen, iron, the building blocks of planets and people. You are made of stardust. This is not poetry. This is physics. Every atom in your body, except for hydrogen, was forged in the nuclear furnace of a dying star. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it came from stars that exploded long before the sun was born. You are the universe, rearranged. You are ancient matter, temporarily aware of itself. Right now, you are moving through space at extraordinary speed. The Earth spins at over 1,000 miles per hour. It orbits the Sun at 67,000 miles per hour. The Sun orbits the center of the Milky Way at 500,000 miles per hour. And the Milky Way itself is moving through space at 1.3 million miles per hour, pulled by the gravity of distant galaxy clusters. Yet you feel nothing. No wind, no motion, just stillness. This is the paradox of the cosmos. We live in a universe of violent motion, yet we experience it as peace. We are hurtling through the void at speeds that would tear apart anything not held together by gravity, yet we sit here, calm, breathing ancient air, made of recycled stars. Tonight we explore the quiet truths of the infinite, the slow rhythms of the cosmos, the places and phenomena that remind us that the universe, for all its vastness and violence, is also a place of profound stillness. Out there, in the darkness between stars, planets drift alone. They have no sun to orbit, no light to warm them, no star to call home. These are rogue planets, worlds that were ejected from their solar systems by gravitational interactions or that formed independently in the depths of interstellar space. They wander the galaxy in silence, cold and dark, invisible except for the faint heat they still radiate from their formation. Astronomers estimate there may be billions of rogue planets in the Milky Way alone, possibly outnumbering stars. For every star you see in the night sky, there may be dozens of planets drifting unseen in the darkness. These worlds are difficult to detect because they emit no light of their own and reflect no light from a nearby star. They are ghosts, wandering the void. Some rogue planets were once part of solar systems like ours. They formed around a star, perhaps with moons, perhaps with atmospheres, perhaps even with oceans. But something went wrong. A close encounter with another planet, a passing star, a disturbance in the gravitational balance. Whatever the cause, the planet was flung outward, accelerating until it escaped the star's gravity entirely. It became a wanderer, cast out into the cold. Other rogue planets may have formed alone, never knowing the warmth of a sun. In the dense clouds of gas and dust where stars are born, some clumps of matter may collapse under their own gravity, forming planet-sized objects without ever being captured by a star. These orphan worlds are born into darkness and will remain in darkness for billions of years, drifting through the galaxy on slow, lonely orbits. The surface of a rogue planet is unimaginably cold. Without a star to provide warmth, temperatures plummet to just a few degrees above absolute zero. Any atmosphere the planet once had would freeze and fall as snow, covering the surface in layers of frozen nitrogen, methane, or carbon dioxide. The sky would be black, filled with stars but no sun. There would be no day, no night, no seasons, just eternal darkness and cold. Yet these worlds are not entirely dead. Deep beneath the surface, heat from the planet's formation may still linger. Radioactive decay in the core could generate warmth for billions of years. If the planet has a thick atmosphere or an insulating layer of ice, this internal heat could maintain liquid water beneath the surface, creating subsurface oceans like those believed to exist on Europa and Enceladus. Life, if it exists on rogue planets, would be life that never sees the stars. There is something deeply peaceful about rogue planets. They are worlds without urgency, drifting through space at their own pace, untethered from the gravitational dance of a solar system. They are silent, patient, enduring. They will wander the galaxy for trillions of years, long after the stars have burned out, long after the universe has grown cold and dark. They are the ultimate hermits, content in their solitude, asking nothing, needing nothing, simply existing in the quiet of the void. What if the universe has no beginning and no end? What if the Big Bang was not the start of everything, but just one moment in an infinite cycle of expansion and contraction, birth and death, repeated over and over for eternity? This is the idea behind cyclic cosmology, a theory that suggests the universe is eternal, endlessly recycling itself. In the standard model of cosmology, the universe began 13.8 billion years ago in the Big Bang, a moment of infinite density and temperature from which space, time, and matter emerged. The universe has been expanding ever since, and it will continue to expand forever, growing colder and more diffuse, until it reaches a state called heat death, where all stars have burned out, all matter has decayed, and nothing remains but a thin soup of particles drifting through an infinite void. They suggest that the universe undergoes cycles of expansion and contraction. After the Big Bang, the universe expands for billions of years, just as we observe. But eventually, the expansion slows and reverses. The universe begins to contract, pulled back together by gravity. Galaxies collide, stars merge, and everything collapses back into a single point, a big crunch. And then, from the big crunch, a new Big Bang emerges, and the cycle begins again. In this model, the Big Bang was not the beginning of time, but the end of a previous universe and the start of a new one. Before our universe, there was another universe, and before that, another, stretching back infinitely into the past. And after our universe ends, there will be another, and another, stretching forward infinitely into the future. The universe is eternal, but not static. It breathes, expanding and contracting in a cosmic rhythm that has no beginning and no end. Another version of cyclic cosmology involves the concept of a multiverse. In this scenario, our universe is just one bubble in an infinite foam of universes, each one expanding, evolving, and eventually collapsing or fading away. New universes are constantly being born from quantum fluctuations in the fabric of space-time, and old universes are constantly dying. The multiverse as a whole is eternal, even though individual universes have finite lifespans. There is no definitive evidence for cyclic cosmology, and it remains a speculative idea, but it is compelling because it addresses one of the deepest questions in cosmology. What came before the Big Bang? If the universe is cyclic, there is no before. There is only an infinite series of universes, each one emerging from the ashes of the last. The idea of a recycling universe is strangely comforting. It suggests that nothing is ever truly lost, that the end of one universe is the beginning of another, that the cosmos is not marching toward a final cold death, but is instead engaged in an eternal dance of creation and destruction. It is a universe that renews itself, that finds a way to continue, that refuses to end. It is a universe that, like life itself, is resilient, adaptable, and endlessly creative. If you could see in microwaves instead of visible light, the entire sky would glow, not brightly, but with a faint, uniform warmth coming from every direction at once. This is the cosmic microwave background, or CMB, the oldest light in the universe. It has been travelling through space for 13.8 billion years, and it is the afterglow of the Big Bang itself. The CMB was created about 380,000 years after the Big Bang. Before that moment, the universe was too hot and dense for light to travel freely. Photons were constantly scattered by free electrons trapped in a thick fog of plasma. But as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. This process, called recombination, made the universe transparent for the first time. Photons were suddenly free to travel through space, and they have been traveling ever since. Those photons have been stretched by the expansion of the universe. When they were first emitted, they were high-energy gamma rays and X-rays. But over billions of years, as space itself expanded, the wavelengths of the photons stretched with it, shifting down through the spectrum, from gamma rays to X-rays to ultraviolet to visible light to infrared and finally to microwaves. Today, the CMB has a temperature of about 2.7 degrees above absolute zero. The CMB is remarkably uniform. No matter which direction you look in the sky, the temperature is almost exactly the same, varying by only a few parts in 100,000. This uniformity is one of the strongest pieces of evidence for the Big Bang theory. It shows that the early universe was incredibly smooth and homogeneous, with only tiny fluctuations in density that would later grow into galaxies and galaxy clusters. But the CMB is not perfectly uniform. There are tiny temperature variations, hot spots and cold spots, imprinted on the sky in a pattern that looks like a mottled, blotchy map. These variations are the seeds of structure in the universe. Regions that were slightly denser than average had slightly stronger gravity, which pulled in more matter, which increased the gravity further in a runaway process that eventually formed galaxies. The pattern of hot and cold spots in the CMB is a snapshot of the universe when it was only 380,000 years old, a baby picture of the cosmos. Scientists have mapped the CMB with extraordinary precision using satellites like COBE, WMAP and Planck. These maps have allowed cosmologists to measure the age of the universe, the density of matter and dark energy, the rate of expansion and the geometry of space. The CMB is a treasure trove of information, a fossil record of the early universe, preserved in light that has been travelling for nearly 14 billion years. There is something deeply moving about the CMB. It is light from the beginning of time, the first light that could travel freely through the universe. When you tune a radio to a frequency between stations and hear static, about 1% of that static is the CMB, the echo of the Big Bang still reverberating through the cosmos. You are listening to the sound of creation, a whisper from the dawn of time still audible after 13.8 billion years. Imagine a planet made entirely of diamond. Not a planet with diamond deposits, but a world where the entire interior is crystalline carbon compressed under immense pressure into the hardest substance in nature. These are carbon planets, and they may exist in the galaxy, cold and silent, their surfaces covered in graphite and their cores glittering with diamond. Carbon planets form in regions of the galaxy where carbon is more abundant than oxygen. In our solar system, oxygen is more common, so it bonds with silicon to form silicate rocks and with hydrogen to form water. But in carbon-rich environments, carbon bonds with itself, forming graphite, diamond and silicon carbide instead of the familiar rocks and minerals of Earth. The first carbon planet was discovered in 2004, orbiting a pulsar. Since then, astronomers have identified several candidates, though confirming their composition is difficult. These planets are thought to have formed in the early universe when the ratio of carbon to oxygen was higher than it is today. They are ancient worlds, relics of a time when the galaxy was young and the chemistry of planet formation was different. The surface of a carbon planet would be unlike anything in our solar system. Instead of granite and basalt, the crust would be made of graphite and silicon carbide, dark and slippery. There would be no water, no oceans, no atmosphere of oxygen and nitrogen. The sky would be black, and the ground would be hard and lifeless. But beneath the surface, under pressures millions of times greater than Earth's atmosphere, carbon would crystallize into diamond. The core of a carbon planet could be a single, massive diamond, larger than Earth's moon. This diamond would not sparkle, it would be buried deep underground, invisible, surrounded by layers of graphite and carbide. But it would be there, a heart of pure crystal, formed over billions of years by the slow, patient work of pressure and heat. Carbon planets are unlikely to support life as we know it. Life on Earth is based on water and silicate chemistry, and carbon planets have neither. But they are fascinating nonetheless, examples of how diverse planetary systems can be, how the same elements can combine in different ways to create entirely different worlds. There is a quiet beauty in the idea of diamond planets. They are worlds of extreme simplicity, made of a single element arranged in perfect crystalline order. They are cold, dark, and lifeless, but they are also pure, enduring, and beautiful in their own way. They are the universe's hidden gems, scattered through the galaxy, waiting to be discovered. Does the universe have an edge? Is there a place where space ends, where you could reach out and touch the boundary of existence? The answer, according to our best understanding of cosmology, is no. The universe has no edge. But this does not mean it is infinite. It could be finite yet unbounded, curved back on itself, in a way that makes it endless without being limitless. To understand this, imagine the surface of a sphere, like the Earth. If you start walking in one direction, you will never reach an edge. You will just keep walking, eventually returning to your starting point. The surface of the Earth is finite. It has a definite area, but it is unbounded. There is no edge, no boundary, no place where the surface ends. The universe could be similar, but in 3 dimensions instead of 2. If space is curved in a particular way, you could travel in a straight line through the universe and eventually return to where you started, having circumnavigated the entire cosmos. The universe would be finite in volume, but it would have no edge. There would be no outside to the universe, no boundary where space ends and something else begins. This is called a closed universe, and it is one of 3 possible geometries for the universe. The other 2 are a flat universe, which extends infinitely in all directions, and an open universe, which is also infinite but has a saddle-shaped curvature. Current observations suggest that the universe is very close to flat, but the measurements are not precise enough to rule out a slight curvature. If the universe is closed, it would have profound implications. It would mean that the universe is finite, that there is a definite amount of space and a definite number of galaxies. It would also mean that light could, in principle, travel all the way around the universe and return to its starting point, though this would take far longer than the current age of the universe. But even if the universe is flat or open, and therefore infinite, it is still unbounded. There is no edge, no wall, no place where space stops. You could travel forever in any direction and never reach a boundary. The universe simply is, extending in all directions without beginning or end. The idea of an unbounded universe is both unsettling and comforting. It is unsettling because it defies our intuition. We are used to things having edges, having limits. But it is comforting because it means the universe is complete, self-contained, whole. There is no outside, no beyond, no place we are excluded from. The universe is all there is, and we are part of it, fully and completely. There is a deep peace in the idea of a curved, infinite universe. It is a universe that folds back on itself, that contains everything within itself, that needs nothing beyond itself to exist. It is a universe that is both vast and intimate, infinite yet whole, a cosmos that is, in a very real sense, home. The universe builds slowly, stars take millions of years to form, galaxies billions. Black holes grow grain by grain, consuming matter so gradually that their increase is nearly imperceptible. Even light, the fastest thing in existence, takes eons to cross the vast distances between galaxies. Tonight, we explore the patient architects of the cosmos, the forces and objects that shape the universe on timescales so vast they make human history seem like a single heartbeat. Stars are not born quickly. They do not suddenly ignite like matches struck in the dark. They form slowly, over millions of years in the cold depths of molecular clouds, vast regions of gas and dust where temperatures hover just a few degrees above absolute zero. A molecular cloud can be hundreds of light years across and contain enough material to form thousands of stars, but most of the cloud is empty space. The gas is so diffuse that it would be considered a vacuum by Earth standards. Yet gravity is patient. Over time, the cloud begins to collapse. Dense regions attract more gas, becoming denser still, in a slow runaway process that can take 1,000,000 years or more. As the cloud collapses, it fragments into smaller clumps. Each clump continues to collapse under its own gravity, slowly spinning, slowly heating. The center of the clump becomes denser and hotter, compressed by the weight of the gas falling inward. This is a protostar, not yet a true star, but a warm glowing core surrounded by a disk of gas and dust. The protostar continues to grow, accreting material from the surrounding disk. Jets of gas shoot out from the poles, carrying away angular momentum and allowing more material to fall inward. The process is slow, measured in hundreds of thousands of years. The protostar glows with infrared light, invisible to human eyes but detectable by telescopes designed to see through the dust. Eventually, after millions of years, the core of the protostar becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms are forced together under immense pressure and temperature, fusing into helium and releasing energy. This is the moment a star is born. The fusion reactions generate heat and pressure that push outward, balancing the inward pull of gravity. The star reaches equilibrium, and it will remain in this state for billions of years, burning hydrogen in its core. The birth of the star is a testament to the power of patience. Nothing about the process is rushed. Gravity works slowly, pulling gas together grain by grain, atom by atom. The cloud does not hurry. The protostar does not hurry. They simply follow the laws of physics, allowing time to do its work. And eventually, after millions of years of slow, steady accumulation, a new light appears in the darkness. There is something deeply calming about the birth of stars. It reminds us that the most important processes in the universe cannot be rushed, that creation takes time, that patience is not just a virtue but a fundamental principle of the cosmos. Galaxies rotate, but they do so at a pace that makes continental drift look fast. The Milky Way, our home galaxy, completes one full rotation every 225 to 250 million years. This is called a galactic year, and in the entire history of Earth, only about 20 galactic years have passed. The last time the Sun was in its current position in the galaxy, dinosaurs had not yet evolved. The continents were arranged differently. The most complex life on Earth was still confined to the oceans. One galactic year ago, the world was unrecognizable, and one galactic year from now, it will be unrecognizable again. The rotation of a galaxy is not like the rotation of a solid object. A galaxy is not a rigid disk. It is a collection of hundreds of billions of stars, each one orbiting the galactic center at its own speed, determined by its distance from the center and the distribution of mass within the galaxy. Stars closer to the center orbit faster. Stars farther out orbit more slowly. But even the fastest stars take millions of years to complete a single orbit. The Sun orbits the galactic center at about 515,000 miles per hour. This sounds fast, but at a distance of 26,000 light-years from the center, it takes 225 million years to complete the journey. The Sun has made this journey about 20 times since it formed 4.6 billion years ago. Each orbit takes it through different regions of the galaxy, through spiral arms dense with gas and young stars, through quieter inter-arm regions, through clouds of dust and past ancient globular clusters. As the Sun orbits, it also bobs up and down relative to the galactic plane, oscillating above and below the disk with a period of about 70 million years. This vertical motion is caused by the gravitational pull of the disk itself. When the Sun passes through the plane, it feels a gravitational tug pulling it back, like a weight on a spring. It overshoots, rises above the plane, slows, and then falls back down, crossing the plane again and continuing to the other side. The slow rotation of galaxies is a reminder of the vast scales of the universe. We think of galaxies as dynamic, active objects, and they are. But their dynamism plays out over timescales so long that they appear frozen to us. A photograph of a galaxy today would look identical to a photograph taken 1,000 years ago, or even 1,000,000 years ago. The changes are real, but they are slow, patient, measured in the deep time of the cosmos. There is a profound peace in the galactic rotation. The stars do not rush. They follow their orbits year after year, millennium after millennium, eon after eon. They are part of a grand, slow dance, a cosmic ballet that has been playing out for billions of years and will continue for billions more. Black holes are often portrayed as violent, destructive forces, tearing apart stars and consuming everything that comes near them. And they can be violent, especially when they are actively feeding. But most of the time, black holes grow slowly, patiently, accumulating mass grain by grain over billions of years. But the rate of accretion is usually very slow. Most black holes are starved, surrounded by empty space with very little material nearby to consume. They sit in the darkness, waiting, pulling in the occasional atom, the rare molecule of gas, growing imperceptibly. Supermassive black holes, the giants that lurk at the centers of galaxies, can have masses of millions or even billions of times the mass of the Sun. But they did not start out that way. They began as smaller black holes, perhaps only a few dozen or a few hundred solar masses, formed from the collapse of massive stars in the early universe. Over billions of years they grew, consuming gas clouds, merging with other black holes, slowly accumulating mass. The growth is not steady. A black hole may go through periods of rapid growth, when a large cloud of gas falls into the galactic center, or when two galaxies merge and their central black holes combine. During these periods, the black hole can double or triple its mass in a relatively short time, a few million years. But these periods are rare. Most of the time the black hole grows slowly, adding a fraction of a solar mass per million years. The black hole at the center of the Milky Way, Sagittarius A, has a mass of about 4.1 million solar masses. It is currently very quiet, accreting only a tiny amount of material. At its current rate, it would take trillions of years to double its mass. The black hole is patient. It has all the time in the universe. When a black hole does feed, the process is spectacular. Matter falling toward the black hole forms an accretion disk, a swirling vortex of gas heated to millions of degrees by friction and compression. The disk glows brightly, emitting X-rays and gamma rays. Jets of particles shoot out from the poles, accelerated to nearly the speed of light by magnetic fields. The black hole becomes a quasar, one of the brightest objects in the universe, visible across billions of light years. But even this violence is temporary. Eventually, the black hole consumes all the nearby material and the accretion disk fades. The jets shut off, the quasar dims and disappears. The black hole returns to its quiet state, waiting in the darkness for the next meal, which may not come for millions of years. There is something strangely peaceful about the slow growth of black holes. They are not in a hurry. They do not need to be. They are among the most patient objects in the universe, content to wait for billions of years, slowly accumulating mass, slowly growing, knowing that time is on their side. The universe is expanding. This is not a theory or a hypothesis. It is an observed fact, confirmed by decades of measurements. Galaxies are moving away from us, and the farther away they are, the faster they are receding. Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. The expansion was discovered in the 1920s by astronomer Edwin Hubble, who measured the distances and velocities of galaxies and found a clear relationship. The more distant a galaxy, the faster it was moving away. This relationship, now called Hubble's law, was the first evidence that the universe is not static but dynamic, changing over time. The expansion is not galaxies moving through space. It is space itself expanding. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move apart, not because they are traveling across the surface of the balloon, but because the surface itself is stretching. The universe works the same way. Galaxies are not moving through space. They are being carried by the expansion of space. The rate of expansion is described by the Hubble constant, which tells us how fast space is stretching. Current measurements suggest that space is expanding at about 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, the recession velocity increases by 70 kilometers per second. A galaxy 100 million light-years away is receding at about 2,000 kilometers per second. A galaxy a billion light-years away is receding at 20,000 kilometers per second. The expansion is accelerating. This was discovered in the 1990s, when astronomers measured the distances and velocities of distant supernovae and found that the expansion rate was increasing over time. This acceleration is driven by dark energy, a mysterious force that permeates all of space and pushes galaxies apart. Dark energy makes up about 68% of the total energy content of the universe, but we do not know what it is or why it exists. The expansion of the universe has profound implications for the future. If the expansion continues to accelerate, galaxies will move farther and farther apart, eventually receding faster than the speed of light. This does not violate relativity. Nothing is moving through space faster than light, but space itself can expand at any rate. Eventually, distant galaxies will disappear beyond the cosmic horizon, their light stretched to infinite wavelengths forever unreachable. In the far future, trillions of years from now, the universe will be a lonely place. Galaxies will be isolated, separated by vast, ever-growing distances. The night sky will be dark, with only the stars of the local galaxy visible. The cosmic microwave background will fade to nothing, its photons stretched to wavelengths longer than the observable universe. The expansion will continue, relentless and unstoppable, until the universe is cold, dark, and empty. But that is trillions of years away. For now, the expansion is gentle, patient, unhurried. Space stretches slowly, carrying galaxies apart at a pace that is imperceptible on human timescales. The universe is not in a rush. It has all the time in the world, literally. Neutron stars are the remnants of massive stars that exploded as supernovae. When a star more than 8 times the mass of the Sun exhausts its nuclear fuel, its core collapses in a fraction of a second, compressing matter to densities so extreme that protons and electrons are forced together to form neutrons. The result is a neutron star, an object about 20 kilometers across but with a mass greater than the Sun. Neutron stars are incredibly dense. A teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is so strong that if you dropped an object from a height of 1 meter, it would hit the ground at a significant fraction of the speed of light. The magnetic fields are the strongest in the universe, trillions of times stronger than Earth's magnetic field. When neutron stars first form, they spin rapidly, sometimes hundreds of times per second. This is due to conservation of angular momentum. As the core of the star collapses, it spins faster, like a figure skater pulling in their arms. Some neutron stars emit beams of radio waves from their magnetic poles, and as the star spins, these beams sweep across space like a lighthouse. If the beam happens to point toward Earth, we detect regular pulses of radio waves. These are pulsars, and they are among the most precise clocks in the universe. But neutron stars do not spin forever. Over time, they lose energy through the emission of electromagnetic radiation and gravitational waves. The rotation slows gradually, imperceptibly. A pulsar that spins 100 times per second today might slow to 99.9999 times per second over 1 million years. The change is tiny, but it is real, and it is relentless. Eventually, after billions of years, the neutron star will slow to a crawl, spinning only once every few seconds or even once every few minutes. It will no longer emit radio pulses, and it will fade from view, becoming a dark, silent remnant, invisible except for its gravitational influence. It will continue to exist, unchanged, for trillions of years, one of the most stable objects in the universe. Some neutron stars are part of binary systems, orbiting another star or another neutron star. In these systems, the neutron star can accrete material from its companion, pulling gas onto its surface. The gas heats up and emits X-rays, making the neutron star visible again. But the accretion is slow, and the neutron star grows only slightly, adding a tiny fraction of its mass over millions of years. There is a deep stillness in neutron stars. They are remnants of violent explosions, but they themselves are quiet, patient, enduring. They spin in the darkness, slowly losing energy, slowly fading, but never disappearing. They are monuments to the end of stellar life, proof that even in death, stars leave behind something permanent, something that will outlast everything else. On the largest scales, the universe is not uniform. Galaxies are not scattered randomly through space. They are arranged in a vast, intricate structure called the cosmic web, a network of filaments, balls, and voids that stretches across billions of light years. The cosmic web formed over billions of years, shaped by gravity. In the early universe, matter was distributed almost uniformly, with only tiny fluctuations in density. But gravity amplified these fluctuations. Regions that were slightly denser than average attracted more matter, becoming denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming voids. Over time, matter flowed along the gravitational gradients, streaming from low-density regions to high-density regions. The result was a network of filaments, long, thin strands of galaxies and dark matter, connected at nodes where multiple filaments intersect. Between the filaments are voids, vast empty regions containing very few galaxies. The filaments are enormous. Some stretch for hundreds of millions of light years, containing thousands of galaxies. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, is a filament over 10 billion light years long. It is so large that light takes 10 billion years to travel from one end to the other. the cosmic web is still evolving. Galaxies continue to flow along the filaments pulled by gravity toward the densest regions. Clusters of galaxies grow larger as more galaxies fall into them. Voids expand as matter is pulled out of them. The process is slow, playing out over billions of years, but it is ongoing. The cosmic web is a reminder that the universe is not static. It is a dynamic, evolving structure, shaped by gravity over vast timescales. The web we see today is different from the web that existed a billion years ago, and it will be different again a billion years from now. But the changes are slow, patient, measured in the deep time of the cosmos. There is a quiet beauty in the cosmic web. It is the largest structure in the universe, a pattern woven by gravity over billions of years. It is a testament to the power of simple forces acting over vast scales and time scales to create complexity and order. The cosmic web is the universe's architecture, the framework on which everything else is built. The universe contains extremes that defy imagination, temperatures so cold that atoms barely move, voids so empty that you could travel for hundreds of millions of light years without encountering a single galaxy, objects so dense that a sugar cube-sized piece would weigh as much as all of humanity. Yet these extremes exist in silence, in stillness, in a state of profound cosmic calm. Tonight we explore the quiet extremes of the universe, the places and phenomena that push the boundaries of physics while remaining utterly peacefully still. The coldest natural place in the known universe is the Boomerang Nebula, a cloud of gas and dust about 5,000 light-years from Earth. Its temperature is 1 degree above absolute zero, negative 272 degrees Celsius, or 1 Kelvin. This is colder than the cosmic microwave background radiation that fills all of space, colder than anything else we have found in nature. The Boomerang Nebula is cold because it is expanding. It was created by a dying star that ejected its outer layers into space. As the gas expands, it cools, just as the air in a spray can cool when you release the pressure. But the expansion in the Boomerang Nebula is extraordinarily rapid. The gas is moving outward at about 600,000 kilometers per hour. This rapid expansion has cooled the gas to temperatures lower than anywhere else in the cosmos. At temperatures this close to absolute zero, matter behaves strangely. Atoms move incredibly slowly, almost coming to a complete stop. Quantum effects become important. In laboratories on Earth, scientists have cooled atoms to even lower temperatures, billionths of a degree above absolute zero, and observed bizarre phenomena like Bose-Einstein condensates, where thousands of atoms behave as a single quantum entity. But in the Boomerang Nebula, the cold is natural, not artificial. It is the result of a dying star's last breath, a final exhalation of gas into the void. The nebula will not remain this cold forever. Eventually, the expansion will slow and the gas will warm slightly, heated by the cosmic microwave background and by starlight from distant stars. But for now, it is the coldest place in the universe, a frozen monument to stellar death. There is something peaceful about extreme cold. At temperatures near absolute zero, everything slows down. Atoms barely vibrate. Chemical reactions cease. Time itself seems to slow. The Boomerang Nebula is a place of profound stillness, where the universe is cooled to the point of near-perfect quiet. The concept of absolute zero, 0 Kelvin, negative 273.15 degrees Celsius, is the theoretical lower limit of temperature. It is the point at which atoms would have no thermal energy at all, no motion, no vibration. But absolute zero cannot be reached. The laws of quantum mechanics prevent it. Even at absolute zero, atoms would retain a tiny amount of energy, called zero-point energy, due to the uncertainty principle. They would still vibrate, just barely, in the quantum ground state. The Boomerang Nebula will never reach absolute zero, nothing in the universe will. But it comes closer than anything else we have found, a natural laboratory for studying matter at the edge of stillness, at the boundary between motion and perfect rest. The universe is not evenly filled with galaxies. There are regions where galaxies cluster together in great walls and filaments, and there are regions where galaxies are almost entirely absent. These empty regions are called cosmic voids, and they are among the largest structures in the universe. The largest known void is the KBC void, which may be up to 2 billion light-years across. If you were in the center of this void, you would see very few galaxies in any direction. The nearest galaxy might be hundreds of millions of light-years away. The night sky would be almost empty, with only a handful of faint smudges visible even with the most powerful telescopes. Voids are not completely empty. They contain some galaxies, but far fewer than average. The density of matter in a void is about 10 to 20% of the average density of the universe. This might not sound like much of a difference, but on cosmic scales it is enormous. Voids are underdense regions, places where gravity has pulled matter out and into the surrounding filaments and walls. Voids form naturally from the initial density fluctuations in the early universe. Regions that were slightly less dense than average lost matter to their denser neighbours. Over billions of years, these regions became more and more empty, expanding as matter flowed out of them. The result is a cosmic web of filaments and voids, with galaxies concentrated along the filaments and vast empty spaces in between. The voids are expanding. As the universe expands, the voids grow larger, and the filaments between them stretch. Eventually, in the far future, the voids will dominate the universe. Galaxies will be isolated in small clusters, separated by vast, ever-growing expanses of empty space. The universe will become a lonelier place, with more emptiness than matter. But for now, the voids are simply quiet. They are regions of profound emptiness, where the universe is almost as it was in the beginning, smooth, uniform, undisturbed. There are no stars in the voids, no planets, no life, just space, stretching for hundreds of millions of light-years, filled with nothing but the faint glow of the cosmic microwave background and the occasional stray atom. There is a deep peace in the voids. They are places where the universe is at its simplest, where complexity has been stripped away, leaving only emptiness and silence. They are the cosmic equivalent of a blank canvas, a reminder that the universe is mostly empty, that matter is the exception, not the rule. When a star like the Sun exhausts its nuclear fuel, it does not explode. It simply stops burning. The outer layers drift away, forming a planetary nebula, and the core is left behind, a white dwarf. A dense, hot remnant about the size of Earth, but with a mass comparable to the Sun. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh about 15 tons. The atoms are packed so tightly that electrons are forced into a degenerate state, where they resist further compression through quantum pressure rather than thermal pressure. This electron degeneracy pressure is what holds the white dwarf up against gravity. A newly formed white dwarf is hot, with surface temperatures of 100,000 degrees Celsius or more. It glows with a brilliant white light, hence the name. But it has no source of energy. It is not fusing hydrogen or helium or any other element. It is simply radiating away the heat left over from its previous life as a star. The white dwarf cools slowly. Over millions of years, it fades from white to yellow to red, becoming dimmer and dimmer. Eventually, after billions of years, it will cool to the point where it no longer emits visible light. It will become a black dwarf, a cold, dark cinder, invisible except for its gravitational influence. No black dwarfs exist yet. The universe is only 13.8 billion years old, and even the oldest white dwarfs have not had time to cool completely. The first black dwarfs will not appear for trillions of years, long after the last stars have burned out, long after the universe has grown cold and dark. White dwarfs are among the most stable objects in the universe. They do not change, do not evolve, do not do anything except slowly radiate away their heat. They are the end state of stellar evolution for most stars, the final resting place for stars that are not massive enough to become neutron stars or black holes. There is something deeply calming about white dwarfs. They are remnants of stellar death, but they are not violent or destructive. They are simply fading embers, cooling slowly, patiently, over timescales that dwarf the age of the universe. They are proof that even in death, stars leave behind something enduring, something that will persist for trillions of years. Space is often called a vacuum, and it is, by Earth standards, but it is not completely empty. Between the stars there is gas, mostly hydrogen, along with trace amounts of helium and heavier elements, but the density is incredibly low. In interstellar space, there might be 1 atom per cubic centimeter. In the voids between galaxies, the density drops to 1 atom per cubic meter, or less. This is emptier than the best vacuum we can create in laboratories on Earth. It is emptier than the inside of a cathode ray tube, emptier than the vacuum chambers used to test spacecraft. It is, by any reasonable standard, nothing. In this near-perfect vacuum, sound cannot travel. Sound is a vibration of matter, a wave that propagates through a medium by compressing and rarefying the material. In air, sound travels at about 340 meters per second. In water, it travels faster. In solids, faster still. But in the vacuum of space, there is no medium for sound to travel through. There is only silence. This silence is absolute. If a star exploded a light year away, you would see the flash of light, but you would hear nothing. If 2 black holes collided, releasing more energy in a fraction of a second than the sun will emit in its entire lifetime, you would detect gravitational waves, but you would hear no sound. Space is silent, not because there are no events, but because there is no air to carry the vibrations. The silence of space is profound. On Earth we are surrounded by sound, the hum of traffic, the rustle of wind, the chirping of birds, the murmur of voices. Even in the quietest places there is always some sound, some vibration of air. But in space there is nothing, just silence, stretching for light years in every direction. This silence is not empty though. Space is filled with light, starlight, the glow of nebulae, the cosmic microwave background. It is filled with particles, cosmic rays, neutrinos, photons. It is filled with fields, gravitational fields, magnetic fields, the quantum fields that underlie all of reality. But it is silent because sound requires matter, and matter is sparse. There is a deep peace in the silence of space. It is a reminder that the universe is not noisy, not chaotic, not filled with sound and fury. It is quiet, patient, still. The events that shape the cosmos, the birth of stars, the collision of galaxies, the expansion of space all happen in silence, witnessed only by the light they emit and the gravitational waves they create. Brown dwarfs are objects that fall between planets and stars. They are more massive than planets, at least 13 times the mass of Jupiter, but not massive enough to sustain hydrogen fusion in their cores. They are failed stars, objects that almost became stars but did not quite make it. When a brown dwarf forms, it follows the same process as a star. A cloud of gas collapses under its own gravity, forming a protostar. The protostar heats up as it accretes material. But if the mass is below about 0.08 solar masses, about 80 times the mass of Jupiter, the core never gets hot enough to ignite hydrogen fusion. The object stops growing, stops heating, and begins to cool. Brown dwarfs do produce some energy, but not from hydrogen fusion. They fuse deuterium, a heavy isotope of hydrogen, in their cores. This produces a small amount of energy, enough to make the brown dwarf glow faintly in infrared light. But deuterium is rare, and the fusion process is short-lived. After a few million years, the deuterium is exhausted, and the brown dwarf stops producing energy. It becomes a cooling ember, slowly radiating away its heat. Brown dwarfs are difficult to detect. They are dim, emitting most of their light in the infrared, and they are small, only slightly larger than Jupiter. They do not shine brightly like stars, and they do not reflect much light like planets. They are ghosts lurking in the darkness between stars, invisible to most telescopes. Astronomers estimate there may be billions of brown dwarfs in the Milky Way, possibly outnumbering stars. They are the most common type of substellar object, but they are also the least understood. We do not know how many there are, how they form, or what role they play in the galaxy. They are the forgotten objects of the cosmos, too small to be stars, too large to be planets, drifting in the darkness. Brown dwarfs cool slowly over billions of years. The hottest brown dwarfs, freshly formed, have surface temperatures of over 2,000 degrees Celsius. The coolest, billions of years old, have temperatures below 100 degrees Celsius, cooler than boiling water. Eventually, they will cool to the temperature of interstellar space, becoming invisible, indistinguishable from the void. There is a quiet sadness in brown dwarfs. They are failed stars, objects that almost achieved fusion but fell just short. They are the universe's near misses, reminders that not everything reaches its potential. But they are also patient, enduring, slowly fading into the darkness, content in their failure, asking nothing, needing nothing. In the gravitational dance between two massive objects, like the Earth and the Moon or the Earth and the Sun, there are special locations where the gravitational forces balance perfectly. These are called Lagrange points, and they are places of profound stillness in an otherwise dynamic system. There are 5 Lagrange points in any two-body system. 3 of them, L1, L2, and L3, lie along the line connecting the two bodies. The other 2, L4 and L5, form equilateral triangles with the two bodies. At these points, the gravitational pull of the two bodies and the centrifugal force of the rotating system balance exactly, creating a stable or semi-stable equilibrium. An object placed at a Lagrange point will remain there, held in place by the balance of forces. It does not need to expend energy to stay in position. It simply sits motionless relative to the two bodies as the system rotates around it. This makes Lagrange points ideal locations for spacecraft and space telescopes. The James Webb Space Telescope orbits the Sun-Earth L2 point, about 1.5 million kilometers from Earth. At this location, the telescope can keep its instruments cold, shielded from the Sun and Earth by a large sun shield, while remaining in constant communication with Earth. The telescope does not orbit Earth, it orbits the Sun, but at a distance and speed such that it remains near the L2 point, moving with Earth as Earth orbits the Sun. Lagrange points are not perfectly stable. L1, 2, and L3 are saddle points, stable in some directions but unstable in others. A spacecraft at one of these points will drift away if left unattended, so small thrusters are needed to keep it in place. But L4 and L5 are stable. Objects at these points will remain there indefinitely, even if slightly perturbed. This is why L4 and L5 points often accumulate debris, asteroids, dust, and other material that has drifted into these gravitational wells and become trapped. The Earth-Sun L4 and L5 points are home to clouds of dust and possibly small asteroids, though none have been definitively confirmed. The Jupiter-Sun L4 and L5 points are home to the Trojan asteroids, two large groups of asteroids that orbit the Sun in the same orbit as Jupiter, 60 degrees ahead and 60 degrees behind. These asteroids have been trapped at the L4 and L5 points for billions of years, stable and unchanging. There is a deep stillness at Lagrange points. They are places where motion and gravity balance, where forces cancel out, where an object can rest without effort. They are the cosmic equivalent of a calm spot in a turbulent river, a place where you can stop and rest, held in place by the currents around you. They are reminders that even in a dynamic, ever-changing universe, there are places of stillness, places where the chaos resolves into perfect balance. Some objects in the universe have existed for nearly as long as the universe itself. They have witnessed the formation of galaxies, the birth and death of countless stars, the slow evolution of the cosmos from a hot, dense state to the cold, vast expanse we see today. These are the ancient witnesses: globular clusters, quasars, the first galaxies, objects that carry within them the memory of the early universe. Tonight, we visit these ancient structures and contemplate the deep time they represent. Globular clusters are among the oldest objects in the universe. These dense, spherical collections of stars orbit galaxies in the halo, far from the galactic disk. Each cluster contains hundreds of thousands to millions of stars, all packed into a region only a few dozen light years across. The stars in globular clusters are ancient, typically 10 to 13 billion years old, formed when the universe was young. The Milky Way has about 150 known globular clusters, and they are scattered throughout the halo, orbiting the galaxy on highly elliptical paths. Some pass through the galactic disk, while others remain far out in the halo, never approaching the center. These clusters are relics from the early days of galaxy formation, survivors from a time when the Milky Way was still assembling itself from smaller structures. The stars in globular clusters are metal poor, meaning they contain very few elements heavier than hydrogen and helium. This is because they formed before many generations of stars had lived and died, before supernovae had enriched the interstellar medium with heavy elements. The low metallicity of globular cluster stars is one of the key pieces of evidence for their great age. Looking at a globular cluster is like looking back in time. The stars you see are nearly as old as the universe itself. They have been shining for over 10 billion years, and they will continue to shine for billions more. They are witnesses to the entire history of the galaxy, silent observers of the slow dance of cosmic evolution. The cores of globular clusters are incredibly dense. In the center of a cluster, stars can be separated by distances of only a light week or so, far closer than stars in the Sun's neighborhood. If Earth were located in the core of a globular cluster, the night sky would be spectacular. Thousands of stars would be brighter than Venus, and there would be no true darkness, just a perpetual twilight filled with starlight. But despite their density, globular clusters are stable. The stars orbit the cluster's center of mass in a complex, chaotic dance, but the cluster as a whole remains intact. Gravitational interactions between stars are rare, and when they do occur, they usually result in one star being ejected from the cluster rather than a collision. The cluster evolves slowly, losing stars over billions of years, but it endures. There is a deep peace in globular clusters. They are ancient, stable, unchanging on human timescales. They have existed for nearly the entire history of the universe, and they will continue to exist for billions of years to come. They are monuments to the endurance of structure, proof that even in a dynamic, evolving universe, some things persist. The first galaxies formed about 200 to 400 million years after the Big Bang. during a period called the Cosmic Dawn. Before this time, the universe was dark. There were no stars, no galaxies, just clouds of hydrogen and helium gas slowly collapsing under gravity. But eventually, the first stars ignited, and the first galaxies began to shine. These early galaxies were small, much smaller than the Milky Way. They contained only a few million to a few billion stars compared to the hundreds of billions in a modern galaxy. But they were incredibly bright for their size, filled with massive hot stars that burned fiercely and died quickly in supernova explosions. The light from these first galaxies has been traveling through space for over 13 billion years. It has been stretched by the expansion of the universe, shifted from ultraviolet and visible light into the infrared. This is why we need infrared telescopes like the James Webb Space Telescope to see them. The galaxies themselves are long gone, merged and absorbed into larger structures, but their light remains a fossil record of the cosmic dawn. Observing the first galaxies is like looking at baby pictures of the universe. We see the cosmos when it was young, when the first structures were just beginning to form, when the universe was transitioning from a smooth, uniform state to the complex, structured state we see today. These galaxies are the seeds from which all modern galaxies grew. The first galaxies were also responsible for reionizing the universe. Before they formed, the universe was filled with neutral hydrogen gas, which is opaque to ultraviolet light. But the intense radiation from the first stars ionized this gas, stripping electrons from hydrogen atoms and making the universe transparent. This period, called the Epoch of Reionization, lasted from about 200 million to 1 billion years after the Big Bang. Studying the first galaxies is one of the frontiers of modern astronomy. We are still discovering new galaxies from this era, pushing the limits of our telescopes to see farther and farther back in time. Each new discovery adds to our understanding of how galaxies form and evolve, how the universe transitioned from darkness to light. There is something humbling about the first galaxies. They are so distant, so ancient, but their light has been traveling for longer than Earth has existed. They are windows into a time before our solar system, before our galaxy as we know it, before most of the stars we see in the night sky. They are the earliest witnesses, the first lights in the cosmic darkness. Quasars are among the brightest objects in the universe. They are powered by supermassive black holes at the centers of galaxies, accreting matter at prodigious rates and releasing enormous amounts of energy. A single quasar can outshine an entire galaxy, emitting more light than 1 trillion stars. Most quasars are incredibly distant, located billions of light years away. This means we are seeing them as they were billions of years ago, when the universe was young. Quasars were most common when the universe was between 1 and 3 billion years old, during a period of intense galaxy formation and black hole growth. Today, quasars are rare. Most supermassive black holes have consumed the gas in their vicinity and have gone quiet. The light from a quasar has been traveling for billions of years to reach us. It has passed through vast stretches of intergalactic space, through clouds of gas and dust, through the expanding fabric of space-time itself. By the time it reaches our telescopes, it has been redshifted, stretched to longer wavelengths by the expansion of the universe. Quasars are time machines. When we observe a quasar 10 billion light years away, we are seeing it as it was 10 billion years ago, when the universe was less than a quarter of its current age. We are looking back in time, witnessing events that happened long before the Sun and Earth existed. The most distant quasar known is over 13 billion light years away. Its light was emitted when the universe was only 670 million years old, during the Epoch of Reionization. This quasar contains a supermassive black hole with a mass of about 1.6 billion solar masses. How such a massive black hole formed so early in the universe is still a mystery. one of the many puzzles that quasars present. Quasars also serve as cosmic lighthouses, illuminating the gas between galaxies. As quasar light travels through space, it passes through clouds of hydrogen gas, which absorb specific wavelengths of light. By analyzing the absorption lines in a quasar's spectrum, astronomers can map the distribution of gas in the early universe, tracing the cosmic web and studying the conditions that led to galaxy formation. There is a quiet majesty in quasars. They are beacons from the deep past, shining across billions of light years, carrying information about the early universe. They are reminders that the universe was once a very different place, filled with actively feeding black holes and rapidly forming galaxies. They are witnesses to a time of cosmic violence and creation, now visible to us as faint points of light in the distant sky. In the halo of the Milky Way, there is a star called HD 140283, nicknamed the Methuselah star. It is one of the oldest known stars in the universe, with an estimated age of about 14.5 billion years, give or take 800 million years. This is nearly as old as the universe itself, which is 13.8 billion years old. For a while, the Methuselah star caused astronomers some concern. Early estimates of its age suggested it might be older than the universe, which would be impossible. But refined measurements, taking into account uncertainties in distance and composition, have brought the age estimate into line with the age of the universe. The star is old, but not impossibly old. The Methuselah star is a subgiant, a star that has exhausted the hydrogen in its core and is beginning to expand. It is metal poor, containing very few elements heavier than hydrogen and helium, which is consistent with its great age. It formed in the early universe, before many generations of stars had enriched the interstellar medium with heavy elements. This star has been shining for nearly the entire history of the universe. It formed when the first galaxies were just beginning to assemble, when the cosmic microwave background was still hot enough to glow visibly. It has witnessed the formation of the Milky Way, the birth of the Sun, the evolution of life on Earth. It is a relic from the beginning, a survivor from the dawn of time. The Methuselah star is not unique. There are likely many other stars of similar age in the halo of the Milky Way and in other galaxies, but it is one of the few we have identified and studied in detail. It is a window into the early universe, a living fossil that carries within it the chemical signature of the first generations of stars. Studying ancient stars like the Methuselah star helps astronomers understand the early universe. By analyzing the star's composition, we can learn about the conditions in which it formed, the types of stars that preceded it, and the processes that enriched the early universe with heavy elements. Each ancient star is a piece of the cosmic puzzle, a clue to the history of the universe. There is something deeply moving about the Methuselah star. It is a reminder that some things endure, that even in a universe of constant change, there are objects that have persisted for nearly the entire history of time. It is a witness to everything, a silent observer that has seen the universe evolve from its infancy to its current state. We have already discussed the cosmic microwave background in Chapter 1, but it deserves another mention here, as it is the oldest observable light in the universe. The CMB is a snapshot of the universe when it was only 380,000 years old, a baby picture of the cosmos. The photons in the CMB have been travelling for 13.8 billion years. They have crossed the entire observable universe, stretched by the expansion of space from high-energy gamma rays to low-energy microwaves. They are the oldest light we can see, the first light that could travel freely through the universe. When we observe the CMB, we are looking at the surface of last scattering, the moment when the universe became transparent and photons were freed from the fog of plasma. This surface is like a wall surrounding us, located about 46 billion light-years away in all directions. We cannot see beyond this wall, because before the surface of last scattering, the universe was opaque. The CMB is remarkably uniform with a temperature of about 2.725 Kelvin in all directions, but there are tiny fluctuations, hot spots and cold spots that vary by only a few parts in 100 K. These fluctuations are the seeds of all structure in the universe. The galaxies, galaxy clusters, and cosmic web that we see today all grew from these tiny density variations. The CMB is also a source of information about the fundamental properties of the universe. By analyzing the pattern of fluctuations, cosmologists can measure the age of the universe, the density of matter and dark energy, the rate of expansion, and the geometry of space. The CMB is a treasure trove of data, a fossil record of the early universe that continues to yield new insights. There is a profound peace in the CMB. It is the echo of the Big Bang, the afterglow of creation, still visible after 13.8 billion years. It is a reminder that the universe has a history, that it was once very different from what it is today, that it has evolved over vast timescales from a hot, dense state to the cold, vast expanse we inhabit. Red dwarfs are the smallest, coolest, and most common type of star in the universe. They have masses between about 0.08 and 0.5 solar masses, and they burn their fuel so slowly that they can live for trillions of years, far longer than the current age of the universe. The Sun, by comparison, will live for about 10 billion years. Massive stars live for only a few million years, but red dwarfs are so small and so cool that they fuse hydrogen at an incredibly slow rate. They are the tortoises of the stellar world, slow and steady, outlasting everything else. No red dwarf has ever died. The universe is only 13.8 billion years old, and even the oldest red dwarfs have barely begun their lives. They will continue to shine for hundreds of billions, even trillions of years, long after the Sun has become a white dwarf, long after all the massive stars have exploded as supernovae. Red dwarfs are also fully convective, meaning their interiors are constantly mixed by convection currents. This allows them to use all of their hydrogen fuel, not just the hydrogen in the core. When a red dwarf finally exhausts its fuel, it will not expand into a red giant like the Sun. It will simply fade, slowly cooling and dimming until it becomes a white dwarf. The first red dwarfs to die will not appear for trillions of years. By that time, the universe will be a very different place. Most stars will have burned out, galaxies will have merged and dispersed, and the universe will be cold and dark. But the red dwarfs will still be shining, the last lights in a dying cosmos. Red dwarfs are the ultimate survivors. They are patient, efficient, and enduring. They do not burn brightly, but they burn for a very long time. They are the stars that will outlast all others, the final witnesses to the end of the stelliferous era, the age of stars. There is a quiet strength in red dwarfs. They are not impressive. They are small, dim, and cool, but they are also resilient, capable of surviving for timescales that dwarf the age of the universe. They are proof that patience and efficiency can outlast power and brilliance, that the slow and steady can endure when the fast and bright have long since faded. We have travelled far together, across billions of light years and billions of years of time. We have visited the coldest places in the universe, the emptiest voids, the oldest stars. We have witnessed the slow birth of galaxies, the patient growth of black holes, the eternal dance of cosmic expansion. But now it is time to return home, to the present moment, to the quiet wonder that surrounds us every night when we look up at the stars. This final chapter is about perspective, about our place in the cosmos, and about the peace that comes from understanding how small we are and how connected we are to everything. In 1990, the Voyager 1 spacecraft, then about 6 billion kilometers from Earth, turned its camera back toward home and took a photograph. In that image, Earth appears as a tiny speck, less than a pixel, suspended in a beam of scattered sunlight. This is the pale blue dot, one of the most humbling images ever captured. Carl Sagan, reflecting on this image, wrote about how it shows our planet as a mote of dust suspended in a sunbeam, how every human who has ever lived has lived on that tiny point of light. All our triumphs and tragedies, all our wars and peace treaties, all our art and science, everything has happened on that pale blue dot. The image is a reminder of our cosmic insignificance. Earth is not the center of the universe. It is not even the center of the solar system. It is a small planet orbiting an average star in the outer regions of an ordinary galaxy. There are hundreds of billions of galaxies in the observable universe, each containing hundreds of billions of stars, many of which likely have planets of their own. Earth is one planet among countless trillions. But this insignificance is not depressing. It is liberating. It puts our problems in perspective. The things we worry about, our jobs, our relationships, our daily struggles, are important to us, but they are utterly insignificant on cosmic scales. The universe does not care about our anxieties. It simply is, vast and indifferent, operating according to laws that have nothing to do with human concerns. This perspective can be deeply calming. It reminds us that we are part of something much larger than ourselves, that our lives are brief moments in the vast sweep of cosmic time. It encourages humility, a recognition that we are not the center of everything, that the universe does not revolve around us. At the same time, the pale blue dot reminds us of our connection to the cosmos. We are made of atoms forged in stars. We are the universe's way of knowing itself, conscious beings capable of contemplating our own existence and our place in the infinite. We are small, but we are also remarkable, the product of billions of years of cosmic evolution. There is a quiet peace in accepting our cosmic insignificance. It frees us from the burden of thinking we are the most important thing in the universe. It allows us to appreciate the beauty of existence without needing to be at the center of it. We are here now on this pale blue dot, and that is enough. Astronauts who have seen Earth from space often report a profound shift in perspective, a feeling known as the overview effect. From orbit, Earth appears as a fragile, beautiful sphere, floating in the blackness of space. There are no borders visible, no nations, no divisions, just a single unified planet, home to all of humanity. The overview effect is described as a sense of awe and interconnectedness. Astronauts report feeling a deep emotional connection to Earth and to all life on it. They see the planet as a whole, as a single system, and they recognize how fragile and precious it is. The thin blue line of the atmosphere, the only thing protecting life from the vacuum of space, appears incredibly delicate from orbit. This shift in perspective often leads to a sense of responsibility. Astronauts who have experienced the overview effect frequently become advocates for environmental protection and international cooperation. They have seen firsthand that Earth is a single, interconnected system, that what happens in one part of the planet affects the whole, and that we all share the same home. The overview effect is not limited to astronauts. Anyone who contemplates the images of Earth from space, who thinks deeply about our place in the cosmos, can experience a similar shift in perspective. It is a recognition that we are all passengers on the same spaceship, that we are all connected, that our fates are intertwined. There is something deeply peaceful about the overview effect. It dissolves the artificial boundaries we create between nations, between cultures, between people. It reminds us that we are all human, all part of the same species, all living on the same small planet in the vastness of space. It encourages compassion, cooperation, and a sense of shared responsibility for the future. The overview effect is also a reminder of the rarity and preciousness of life. As far as we know, Earth is the only place in the universe where life exists. We have not yet found life on other planets, though we continue to search. For now, Earth is unique, a living world in a cosmos that is mostly empty and lifeless. This makes our planet, and all the life on it, incredibly valuable. Earth is 4.5 billion years old. This is a timescale so vast that it is difficult to comprehend. If the history of Earth were compressed into a single year, humans would appear only in the last few minutes before midnight on December 31st. All of recorded history would fit into the last few seconds. The rocks beneath our feet are ancient. Some are billions of years old, formed when Earth was young and the surface was still cooling. These rocks have witnessed the entire history of the planet, the formation of the oceans, the rise of the continents, the evolution of life, the mass extinctions, the ice ages. They are silent witnesses to deep time. Geology operates on timescales that dwarf human lifetimes. Mountains rise over millions of years, grain by grain, as tectonic plates collide. Rivers carve canyons over millions of years, cutting through rock layer by layer. Continents drift across the surface of the planet at the speed of fingernail growth, rearranging themselves over hundreds of millions of years. This deep time perspective is humbling. It reminds us that the Earth existed long before we did, and will continue to exist long after we are gone. The planet does not need us. It is patient, enduring, operating on timescales that make human history seem like a brief flicker. But deep time also connects us to the past. The atoms in our bodies have been part of the Earth for billions of years. They have cycled through rocks, oceans, atmosphere, and living organisms countless times. We are made of ancient matter, recycled and rearranged, part of a continuous process that has been happening since the planet formed. There is a deep peace in contemplating geological deep time. It puts our lives in perspective, reminds us that we are part of a much larger story, that the Earth has a history far older and grander than our own. It encourages patience, a recognition that change happens slowly, that the most important processes take time. On a clear night far from city lights, the sky is filled with stars, thousands of them scattered across the darkness, each one a sun like our own, each one potentially surrounded by planets. The night sky is a window into the cosmos, a reminder of the vastness and beauty of the universe. But the night sky is also still. The stars do not move, at least not on human timescales. They appear fixed in their positions, forming the same constellations that ancient peoples saw thousands of years ago. The Big Dipper looks the same today as it did to the ancient Egyptians, the ancient Greeks, the ancient Chinese. This stillness is an illusion. The stars are moving, orbiting the galactic center at hundreds of thousands of miles per hour, but they are so far away that their motion is imperceptible. Over thousands of years, the constellations will change shape as the stars drift relative to each other, but on human timescales, the sky appears unchanging. There is something deeply calming about the stillness of the night sky. It is a constant in a world of change. No matter what happens in our lives, no matter what turmoil or upheaval we experience, the stars are still there, shining as they have for billions of years. They are a reminder that the universe is stable, enduring, reliable. The night sky also connects us to the past. When we look at the stars, we are looking back in time. The light from the nearest star, Proxima Centauri, takes over 4 years to reach us. The light from more distant stars takes decades, centuries, even thousands of years. When we look at the Andromeda Galaxy, we are seeing it as it was 2.5 million years ago, when our ancestors were just beginning to walk upright. The night sky is a time machine, a way of seeing the universe as it was, not as it is. Every photon that enters our eyes has been traveling for years, carrying information about the distant past. The stars we see tonight may no longer exist. Some may have exploded as supernovae, their light not yet reaching us. We are looking at ghosts, at echoes of the past, at a universe that has already changed. There is a quiet wonder in the night sky. It is beautiful, mysterious, and humbling. It reminds us of our place in the cosmos, of the vastness of space and time, of the countless worlds that exist beyond our own. It invites contemplation, curiosity, and a sense of awe at the infinite. We often think of ourselves as separate from the universe, as observers looking out at something external. But this is a false dichotomy. We are not separate from the universe, we are part of it. We are the universe, localized, aware, contemplating itself. Every atom in your body was created in a star or in the Big Bang. The hydrogen in your body is 13.8 billion years old, formed in the first few minutes after the universe began. The carbon, oxygen, and nitrogen were created in the cores of stars that lived and died before the sun was born. The heavier elements, the iron in your blood, the calcium in your bones, were created in supernova explosions, scattered into space, and eventually incorporated into the cloud of gas and dust that formed the solar system. You are made of stardust. This is not a metaphor. It is a literal fact. The atoms in your body have been part of the cosmos for billions of years, cycling through stars, planets, and living organisms. You are ancient matter, temporarily arranged into a conscious being capable of thinking, feeling, and wondering about your own existence. This cosmic perspective is both humbling and empowering. It is humbling because it reminds us that we are not special in the grand scheme of things. We are made of the same stuff as everything else in the universe: stars, planets, rocks, dust. We are subject to the same physical laws, the same forces, the same processes. We are not separate from nature, we are nature. But it is also empowering because it means we are connected to everything. We are part of the cosmic story, participants in the ongoing evolution of the universe. We are the universe's way of knowing itself, of experiencing itself, of contemplating its own existence. In a very real sense, when you look up at the stars, the universe is looking at itself. This perspective dissolves the sense of isolation and separation that many people feel. We are not alone. We are part of a vast, interconnected web of matter and energy stretching across billions of light years and billions of years of time. We are connected to the stars, to the galaxies, to the cosmic microwave background, to the very fabric of space-time itself. There is a deep peace in the cosmic perspective. It reminds us that we belong, that we are home, that we are part of something much larger and more beautiful than ourselves. It encourages gratitude, wonder, and a sense of reverence for the universe and our place in it. We have travelled through space and time, exploring the farthest reaches of the cosmos and the deepest depths of history. But ultimately, all we have is the present moment. The past is gone, the future is uncertain, and the only thing that truly exists is now. This moment, right now, is all there is. You are here, breathing, aware, alive. The atoms in your body are vibrating, your heart is beating, your neurons are firing. You are a temporary arrangement of matter and energy, a brief flicker of consciousness in the vast expanse of cosmic time. But this moment is also eternal. It is the only moment that ever exists. The past is a memory, the future is a projection, but the present is real. It is the interface between what was and what will be, the only point where you can act, where you can experience, where you can be. The universe is not somewhere else. It is here, now, in this moment. The stars are shining, the galaxies are spinning, space is expanding, all right now. The cosmic processes we have discussed, the birth of stars, the growth of black holes, the expansion of space, are all happening in the present moment. The universe is not a static thing. It is a dynamic, evolving process, and you are part of it. There is a profound peace in the present moment. It is the only place where worry and anxiety do not exist. Worry is about the future, regret is about the past, but the present moment is simply what is. When you are fully present, fully aware, you are at peace. The cosmic perspective enhances this peace. When you realize that you are made of stardust, that you are part of the universe, that you are connected to everything, the present moment becomes even more precious. You are here, now, a conscious being in a vast cosmos, able to experience the beauty and wonder of existence. This is the final truth of cosmic stillness, that despite all the motion, all the change, all the vastness and complexity of the universe, there is a deep stillness at the heart of everything. It is the stillness of the present moment, the eternal now, the only place where you truly exist. Take a slow breath. Feel the air entering your lungs, ancient oxygen created in stars billions of years ago. Feel your heartbeat, the rhythm of life, the pulse of the universe within you. You are here, you are now, you are home. Sleep well, traveler. You are part of the infinite, and the infinite is part of you.